All right, so with this one, the trick is to look back at our chart and look for something that kind of looks useful. So let me pull the chart up here. So I'm looking for through these defined power series, and I'm trying to find something that looks like x over 1 plus x squared, or some sort of fraction thing. Clearly this top part doesn't fit the bill, but this bottom one, if I can find a clever manipulation, maybe I can take advantage of this pattern to expand that thing out. So let's replace, well, yeah, so here's going to be our clever manipulation. I'm going to move the x to the outside there. I'm going to leave it as 1 over 1 minus a negative x squared. And that does look like our pattern there, where it's 1 minus something. Kind of think of it like a u substitution. So in the pattern then, so I'm multiplying by x, and then my expansion is going to just fit that 1 over 1 minus x pattern. So 1 plus negative x squared plus negative x squared squared plus negative x squared, negative x squared cubed dot dot dot. And then I just multiply that x in and try to simplify some of the exponents out. So that would give me an x minus x cubed plus x to the 5th minus x to the 7th. And at that point it's like, okay, I can kind of see what's going on here. And so our summation example, I start at n equals 0 to infinity. That looks like I have an alternating sign, so I need to have negative 1, and it's usually either n or n plus 1, whatever is going to give me the correct pattern of plus minus plus minus. So in this case, if I put an n in, that would give me negative 1 to the 0, which is 1, so the first term would be positive, and then negative 1 to the first power would be negative, negative 1 squared would be positive. So that negative 1 to the n would in fact give me the correct alternating sign pattern. And then I need just a formula that'll generate the odd exponent, so 1, 3, 5, 7, and that's a pretty standard 2n plus 1 will generate odd numbers for me there. So there is our expansion of x over 1 plus x squared. Okay, so in this question, the challenge we have is that we're asked to combine this into a single power series. Right now we've got 2 separate power series. But moreover, the problem is that one of our power series starts with n equals 2 and the other one starts with n equals 0. So they're not essentially in phase with each other. We need to figure out a way to get them to match. So one technique is to just expand out the series until we recognize a defined pattern, and then from there try to rewrite what we see into some useful pattern, I guess. So let's start with let's play with the n equals 2 pattern. Let's just see what would happen if I expand that out. Just look at the very first term. So if n equals 2 of this first pattern right there, what would that look like? So that would be 2 times 1 c2 x to the 2 minus 2, which is 2 c2 x to the 0, right? And then the rest of the pattern we'd say, all right, well, let's just absorb that up. That's, by the way, 2c2. And so if I said, all right, well, instead of writing out the next pattern, what if I just say, okay, and then the next term would be n equals 3, starting at n equals 3, and then we would have n times n minus 1 times Cn n x to the n minus 2. And then minus, and since we haven't done anything with the second summation, we're just going to bring that down. And let's see if that actually did anything interesting for us. Alright, so as we're looking at this, what do we notice? And right here we notice that one series has an n minus 2 in it, and the other series has an n plus 1 in it. If we can find a clever way to get those to be the same, then we could find a nice easy way to connect the two patterns. So now we just got to think of a nice indice that would do that for us. So what if in this first set, so this guy right here, what if we replace n with k, and we let k equal n minus 2? And I'm picking the variable that was the exponent, the n minus 2. And in this pattern, what do you think I should let k equal here? So in that case, I think k should equal n plus 1. Okay. So let's combine that and see what happens with that. So we got our 2c2 term from the beginning there. And instead of starting here at n equals 3, this would put me starting at k equals 1. That's 3 minus 2 is 1. Okay. And that would give me an n still, an n minus 1, Cn, and that would give me an x to the k. And then over here, and since I'm trying to manipulate this, let me remind us of those two terms. So this one, since n equals 1, so if I evaluate that at 0, I get k equals 1. Up to infinity. C sub, I just realized I should be switching out my n's and my k's, and that's actually going to change the patterns there. So that's a C sub k. N is going to become k plus 2, and n minus 1 is going to be k plus 1, based on that substitution. Alright, so then minus k equals 1 summation infinity of c to the k minus 1, and this would be k plus 2 of x to the k. So now I got the exponents to match at least. And so now we can combine our summations. So our pattern would become 2c2 plus summation for k equals 1 to infinity. And then we have this nice lovely pattern here of k plus 2, k plus 1 times c of the k plus 2 term minus c of the k plus 1 term, all of that times x to the k power. And so now we found a way to combine that into a single power series.